So like James is very kind to introduce me. My name is Shyam. I work at Gawa. I've been at Gawa for 3 years. I've been working with Haskell for about 15 years. And I have only had to touch the FFI in the last year or so. So that should kind of give you a sense of what the FFI is. It is not something that most people need to deal with. But when you do need to deal with it, it is very useful to be able to. And that will come through here. And most of the time, you'll have a team, and only one of them will need to deal with the FFI. And if you're on my team, that person is me. Hi. All right, so if you read the abstract or the talk announcement, you probably know that the FFI stands for Foreign Function Interface. Let's not start there. Let's start with that working. Oh, the cursor needs to be on the window. So what does the FFI let you do? What is it supposed to let you do? It is supposed to let you do something like this. You have a C program, well, a library stub thing, defines a function that you want to be able to call from Haskell. This is not going to work for a variety of reasons that I will show you, but the idea is you want to be able to put some FFI stuff here. And with this stuff in place, this should just work. And in fact, with this stuff in place that I'll show you, this does in fact just work. GHC is in fact capable of handling C files on the command line. It will build them. It will call GCC. And if you're wondering why it is hello world _HS and _C, it's because you run into linker problems if they're called the same thing. But this is kind of what we want to be able to do. We want to be able to call C functions, call foreign functions from Haskell. For the purpose of this talk, it's going to be C, but there's no reason why it can't be other things. And there are plenty of reasons why you might be wanting to do this. Maybe you've got legacy code that you just have to interrupt with. Maybe some of that code is high-performance scientific computing, which happens to be my use case, where you really don't feel like re-implementing all of those algorithms one after the other. And so you just call in and let them worry about correctness and performance, and you just make calls in. There are plenty of reasons. So what can we do? What does GHC let you do to just have a line up here that lets all of this work? So this is from the Haskell report. So the FFI is standard. It's not a GHC thing. Not just a GHC thing. GHC does provide various extensions and things that let you do more in more varied ways, but the core of the FFI is in the standard. And it's basically, as it says here, it's the ability to describe how to interrupt with other languages, functions defined in another language, and also to let Haskell functions be called from other languages. So there's both the import and the export functionality. And so there's a lot of things that are in here, and the rest of the standard chapter goes into that. But basically, it's to let you map Haskell types to foreign types, Haskell data values to foreign values, functions to functions, as well as manage foreign memory. And the map blah, arrow blah didn't quite work for the last one. And this is basically going to be the structure of this talk, is how do we do these things? So for the example we had, you'll just have to imagine the C function there, which isn't that complicated. You'll have to do that a lot during this talk because slide management of code is not easy for all of this. So we have this huge line up here, foreign, import, C call, unsafe, a string representing hello world, another string, which is hello world, and then the type. We'll go into what all of these are. And I think on a previous Haskell user group, we went into safe versus unsafe. And that discussion lasted for a good half an hour, 45 minutes or so, if I remember. This is the gist of it. You need the foreign function interface pragma. That's what makes the foreign keyword, brings it into scope. And the rest of it is just modifiers to that. But with this one line, the rest of it, if I scroll back to the previous slide, you'll see that it's exactly the same. we can call it, it does work, it does build, and it prints out hello world. So that line is part of this grammar. This is also part of the Haskell standard report, and is basically the jumping point into all of the FFI. So the foreign, that's the entry point. We can either import or export. So this is, you can either import functions from C into Haskell and let you call them there. You can also export Haskell functions to be used in C. The C call is part of the calling convention. It is just a description of how to call functions, pass arguments, get return values, how that stuff is handled. I believe the report only requires that C call and std call are implemented. So C++, JVM, and .NET is more aspirational here on account of the report and not really descriptive.
What's std call?
It's the Windows calling convention. And C-call is the Linux C calling convention, which is not standardized, but it is de facto standardized. Everyone agrees on it. C++ is not at all standardized, and not at all do anyone agree on it. But enough vendors have agreed on the C API to make it work. And in an early version of this talk, I was planning to make a joke where I would go through the first half of the presentation, pretending that I was going to do the Python FFI, and just mock up everything gets converted to string, and I unsafe perform IO the calls to the Python interpreter. That would have resulted in me having to make way too many slides. So I went the more conventional approach.
So earlier you said that this would should work on both. Should be portable, but if you're using Linux, then you have to use ccall, and if you're in Windows, you have to use standard call. So you have to have separate imports for each operating system, or?
So the FFI works on at the level of granularity of the built library. And so it's a question of what was the library built with. You're going to have to build your Haskell code on the appropriate platform and all of that.
But I mean, if you're just trying to import one thing, it sounds like you have to pick a platform rather than your code being portable.
Yeah. So the lowest level answer is you will have to pick the one that is the calling convention of the library that you are trying to import from.
Oh, which is probably platform specific.
Which is platform specific.
Okay.
So you're going to have to do various bits of preprocessor, conditional compilation, or Cabal stuff. And Cabal has support for platform and flags and stuff, so you can make that work. But this highly encourages you to cordon all of that off into a place where you handle all of this, and then forevermore not have to worry about that. Yeah, I think preprocessors how you do it. Yeah.
So it must be fitting, like at least on Windows, will allow you to specify what calling convention, like whether it's CDEC or standard call.
Yeah.
So whichever one, you can choose one, and then regardless of what platform you attempt to link the code on, you can, you'll be confident that it will be called the same, right? So that should help.
There are other parts of this that are also going to be platform dependent, like size of integers and alignment and stuff like that. So there is, in a production grade use of the FFI, you're going to have to do some amount of manual guarding to make sure that stuff actually works. But the bits are all there for you to do. Right, so you have a bunch of calling conventions. Only the first two are actually mandated by the standard. Only the first two are actually implemented, as far as I know, in GHC. And then you have impent and expent. Impent is like a qualified name. So when you do a foreign import, it's going to look up this name as the symbol name that it is going to import. But you can be more specific and specify the header file, and you can do various things. In the rest of this presentation, a lot of the places, I'll leave that string empty, which is both for slide management, but also it's valid, and that means that it will use the name here, which is the Haskell name of the symbol, the Haskell function into which it is imported as the symbol name that it's going to use to look up in the library. Yeah. The last part is the type of the function in Haskell land. And we'll get into that a bit later. But this is kind of a place where you have to be careful because we like Haskell's type safety and GHC verifying that types are sound and all of our various contracts and things are being upheld. That's the leaf of that tree. In that if you don't specify the right type there, those are the facts that GHC is going to use to make sure that the rest of your code is working correctly. So if you mess up there, weird and undefined things will happen. So calling convention, how to do that stuff. Safety is, we can have a longer discussion about safety.
It's not really safety.
It is not really safety. It is in fact unsafety, which is why the conversation goes for 45 minutes. Safety basically is the property of whether a foreign function call can survive a Haskell GC happening while it's in progress. And I'm going to invariably get this wrong, and so someone will have to correct me. If you specify that this call is safe, then it means that you are asking GHC to make sure that no GC happens during the call, I think.
Backwards.
Backwards? See? Perfect.
I think if you say safe, then it does in a different thread.
Yeah. Safe is slower,
I think that's
unsafe is
unsafe.
faster.
Sorry?
That's unsafe.
You sure?
Yeah.
Unsafe is.
Yeah, we can look them up.
Yeah, it's backwards from what you expect.
Is the question, this is safe?
I thought
or
safe
like
meant safe to
do
call
this?
back into Haskell from the thing.
Nope.
This is be safe.
Safe means you're making a promise about this code that it doesn't call back into Haskell.
I don't agree with that.
But we can look this up.
We can-
I think we can look this up if we need it.
We can look it up afterwards. One of them
Well,
is
that's a lot more than I have, so okay.
Anyway, whichever it is. I could be wrong.
one of them is faster, one of them is slower. I'm pretty sure safe is slower and unsafe is faster. One of them may lead to hangs if you try to make a callback. It's about making callbacks into Haskell from C. So if you import a function that you call, and that call in turn makes another call that accesses back into Haskell land, either through data or through other functions that you've stored elsewhere, it can lead to bad things. I've had to use safe exactly once, and that's where a piece of foreign code wanted to be parameterized by a function with which it can print things, and I wanted to provide a function to print things as a function pointer. And so it would be calling from Haskell to C and back into Haskell. It's not common. But yeah, as you can tell, this is why that discussion goes on for a while. Yeah, so this talk.
They named it wrong.
Sorry?
They named it badly, so no one can remember what it means.
Yeah.
I did have it backwards.
Okay.
I feel vindicated, not just because I got it right, but because we had to go through 3 iterations before the Yeah, so this talk we're going to be talking only about CCall and only about importing. I can go into exporting later. There's also a mode of import which does things similar, like meaning like scoped export kind of thing in import wrapper. I don't have slides for that, but I can live code afterwards. None of this talk is live coding because historically that doesn't go well. But we can, if you've got questions, we can try brainstorming stuff afterwards. Right, so we did a hello world function. Let's try something slightly more complicated, namely integers. On the right over there, we have your standard calculator functions, nothing very complicated. And on the left, we have foreign stuff. And so there's a bunch of different things going on here. We're importing Foreign.C.Types, and most of the utilities that we'll see in this talk are in foreign.something. If it's foreign.c, it's specific to the C calling convention. If it's foreign dot and top level stuff, it's more generic than that. In this case, foreign.c.types gives us access to cint and c double. We'll see more of that in the next slide. So here we're importing from a C library, unsafe, the symbol named add, and we're calling it addf. Not quite sure why I called it addf, that's okay. But we're giving it the type cint to iocint. And this is kind of the default type that you give them. Namely, I'm talking about the IO part here, in that it's safe to assume that it's doing side effects. It's doing IO because in C it's possible to do IO anywhere. But here we've done C double to C double, and this is also fine. This will work, and I've called it like that here. This is a pure call. This is a monadic call. And this is where I was talking about get the types right. Because this type that you give here is the foundation of what the rest of the program will be type checked against. If you get that wrong, bad things happen. So it is entirely possible for this function to do side effects. And this will still work because GHC is not going to be able to verify that your C function is not doing side effects. But for a lot of functions, it makes sense because you can verify yourself manually that it's not doing side effects. And you don't want to do monadic shenanigans all the time. And so you can import it as a pure function. But if you import it as a pure function, you run into some use cases where if you have, for example, a return type of unit, then I have seen GHC optimize that out. And so if it's doing side effects, you need to make it a function. It needs to be in IO and so on. So get the types right. Any questions? Yeah.
Is there the wrong number of arguments in the foreign import calls?
That is correct.
Okay.
Thank you. C double to C double to C double. Yeah. Right. So foreign.c.types. Handy screenshot of the Haddix. This is the entire module. N-3 new types of integers and floats and stuff of appropriate sizes. And C file, CF+, and C jump off. And these are the types that are guaranteed by the standard to exist as counterparts to C types. Very handily, the C types are new type wrappers, except for these three down here. They implement show, none, and so on, which is why we were able to do sub F5.3, because that's a integer literal that gets wrapped in a from integral, and that becomes a cint, which is very useful for testing. Yeah?
Are those types the same regardless of the platform or no?
I did think about this. I would assume that it would have to be dependent on platform.
So you get a different type depending on platform, or?
Again, I don't know the exact answer to this, but I would assume that
so.
You would have to.
We had some troubles with Xmonad. People had trouble migrating some of their config files from one architecture to another because they had made some 32-bit assumption about one of these new types.
Ugh.
Yeah.
Ouch.
I think the same convention applies if you're at the FFI in Haskell as it does in C. If you're concerned about sizes of integers, use like concretely sized types. Yeah. I mean,
The word size story in Haskell is one of the few really rough edges.
yeah, these haddocks were pulled off of like Haddock, the website, and so ostensibly this is from a build where C int is in 32. I have not tried building it locally and finding out if it's differently. Right, so numeric types, lots of numeric types. There's pointer diff in there, file position. So what's missing? We're missing pointers, which will be up next, and composite types. And that's kind of it. That's all you really need for building type hierarchies in C. Yeah.
Arrays.
Pointers.
Okay.
And there are utilities to work with arrays so that you don't need to work with them like pointers. I'm not going to go into those, but it's fairly obvious how they work.
What's jump off? Is that what you're pointing?
No, it saves the register, so when you do a jump in C code to go to a different spot in the code, it's like a go-to to allow you to do like go-to cross functions and otherwise like that and all that stuff, right? So you're at a point in the code where you save all the registers, you go to some other point, and you decide, well, I want to go back to this point, right?
It's like set jump long jump.
Right. So yeah, you set the jump buffer at this point, you're somewhere down here, and then you long jump back to this point.
So it's like a continuation.
Kind of like it. Yeah, basically you're just pushing all the registers onto the stack. You're saying, hey, I'm going to execute this code, and then you're looking for them, and then you flip it back again. So, yeah.
Something I've wanted in Haskell.
It's about as bad as go-to.
Sometimes it's what you actually want. It's way better than go-to because it only goes outward.
That's true.
All right.
For something, if it is sometimes do nothing, recursive operation can save you significant time.
Okay. Pointers. Yeah, at the C ABI level, pointers are addresses, and the ABI is asterisk because there is no standard ABI, but by and large, its pointers are addresses. The point being that they're not typed. You would like to have type safety, and so in the Haskell side of modeling pointers, the pointer type in foreign.pointer takes a type. That type is phantom to a certain degree. So you can maintain some type safety. There's also function pointers, which provide some nice utilities when you want to translate between function pointers and actual callable functions. We'll look at an application of that later. So yeah, I mean, it's what you expect. There's a function here that takes an int pointer, and we import it as a pointer to cint arrow IO unit. Yeah, so by and large, pointers come from allocation. And these are the main ways, the most common ways you get memory. Alloca is the one that we like to use, and malloc and free are what we end up having to use in production a lot of the time. So I've got some content over here. I forget if I was supposed to have the C version of this function, but it doesn't really matter. Was it this? It was this, print contents, right. We're importing that function, and just based on these type signatures, we can write this code that is type correct. And so I've got a quick pop quiz. What are we printing? And how much memory are we allocating? based purely on this code that doesn't have a lot going for it.
Seems like you'd be printing some kind of random value, depending on what was there. Yeah, garbage, basically.
Okay, and how much are we allocating?
You allocate
In
the
it.
stack allocation, and for it, and do a heap allocation.
Right.
And then for it.
Right, so the answer is, you're right, it is junk. In all of the examples I tried, it's 0. This is probably a fluke. I wanted it to print junk, wasn't able to get it to do that.
I think Linux 0 initializes pages before it gives them to you, so
I'll buy it.
that might be why.
But you can't trust it.
But yeah,
You can't trust it, yeah. And we allocated 1 C ints worth of memory. And the question is how, like, it's not that surprising to see that it's going to print junk or stuff that's not trustable because we never initialized anything. But the more interesting question is, how did we know how much to allocate? Now, we know cint, right? But where did that come from? And the answer to these questions is partly because I lied. This is not the type signature of alloca and malloc. They are, in fact, qualified by a type class called Storable that gives us all of this information. Free does not have this constraint because free doesn't need to know how big the memory is in order to free it. So the idea of alloca is we give it a function that takes a pointer where we know the type of the pointer from the type of the function. And since we know the type of the pointer, or the type of the value that is supposed to be stored in the memory to which that pointer points to, we can tell how much to allocate. And so alloca will provide that function a blob of memory that has been allocated to the appropriate size. It will pass that pointer to the function, let it run, do whatever. When the function ends, the pointer variable inside the function goes out of scope, and alloca cleans up the memory that it allocated. So it's a safe scoped allocation. And so that's why I said we'd like to use that as much as possible because it provides us a level of memory safety. It's also more efficient because the alloc implementation is optimized. Malloc and free are not quite the foreign imports of malloc and free from the standard library, but they do pretty much the same thing. You can still foreign import malloc and free from the standard library and get that. And sometimes you need to do that.
How do those interact?
Poorly. So the reason I've needed to import free a lot because I've had code bases that provide me a constructor for a thing, but not a destructor. And the constructor used the system version of malloc, and I have to use a system version of free to free it. So in that case, it's as easy as saying foreign import free. And I'm just doing that. You don't want to mix and match memory management idioms. If the C library is going to do it, let it do it. If you're going to do it, preferably use alloca. And there are some abstractions we'll talk about later to bridge over the badness of that all.
When you use the second go, does allocate go after allocate on the stack in Haskell?
No,
Okay.
it does not.
Sorry, what?
Alloca does not allocate on the stack.
Where does it allocate?
So the name just lies. That's fine.
It doesn't say stack anywhere in it.
But
Yeah,
you
but-
see the C function of the same name is right. That's fine.
Wait, are you
Well,
sure?
that's like a historical
Yes.
thing. The reason allocating stack is because the stack wasn't all it was. So you just allocate.
But I think the function still does this thing.
Yeah, the function still does that, but it just
Definitely
means
should.
allocate. It doesn't. You shouldn't.
Oh,
like,
that's
attach
an
the
optional.
meaning
I
to
see.
it.
I see. So it might allocate on the stack. Okay, that's
I
fine.
think, again, don't quote me on this, but if I remember one of Jose's early talks about GHC internal representations, there was, like, none of the things can be allocated on the stack. Like, even the stack is on the heap.
Oh.
So, and it's also not in the GC managed heap either. It's in a separate part of the heap because the memory that Alloca allocates is not GC managed. The pointer itself, like the thunk that represents the pointer A that points to that memory, is GC managed. Alloca only guarantees that when that one goes out of scope, so does the memory that it pointed to. Yeah.
Thank you.
Yeah, so Alloca, malloc, free, not the standard library. Yeah.
So if the pointer is handling, if the destructor for the pointer is straight to memory, can you like move the memory in C and like use that, or should you not?
If the destructor,
So like Alloca gives you a pointer to a block of memory,
yeah,
and the pointer is what reads it. So if you root the reference in C, you use that as like a
meaning if that pointer escapes,
Yeah.
bad things will happen.
Okay. So you don't
There's a lot of bad things will happen here. Like I think it's to be fair, it's mentioned in the haddock for Alloca. It's mentioned in the documentation that the pointer here should not escape.
Okay.
And that's true not just in the Haskell land, but also in the C land. Like you'll get this pointer, and the main thing you're supposed to do with this pointer is pass it to an FFI'd function. That FFI'd function should also not have that pointer escape. And that's one of the cases where you might want to do malloc and free. But I'll also show you an idiom. It's a very proper usage of library functions that will get around this, or it's meant to make that simpler. But yeah, that will get cleaned up after Alloca ends, and so don't let that escape.
So how does Alloca actually work if it doesn't live on the stack?
It's a custom allocator implementation over a subpart of the non-managed part of the heap. So it's just like any other allocator. Different calls to Alloca will reuse different. It won't return the memory immediately. It'll keep them so that it's efficient and so on. It's just an allocator that happens to be more efficient because it knows the type of the thing that it's allocating upfront already. Right, so Storable, highlighted in red, let's look at that. Here is the Storable type class. It is in Foreign.Storable. It has a bunch more methods that we'll look at, but this is like a minimal implementation. So in order for something to be storable, you need to know how big it is, you need to know its alignment, you need to be able to peek and poke, which means peek is read from a pointer's target and poke is write a value into the target of a pointer. Kind of straightforward. So the idea is that the built-in C-types we saw from Foreign.C.Types already implement storable. And so if you're trying to like map a struct, for example, you just make use of the storable instance functions peek and poke for the underlying types. And so just like it seems like you ought to be able to derive storable. And in some cases you can, but bad things happen. Yeah.
How would this work in terms of double or triple indirection?
Give me an example.
Double pointer or triple pointer. I'm trying to dereference multiple pointers to get to the target value before I.
Yeah, this is shallow.
Okay.
Yeah, I believe the storable instance for pointer of A is the storable instance for pointer of A because it's just that one.
Gotcha.
The peek for a pointer A, it will not call peek of A. What?
Yeah,
Yeah,
so if you
on
want to double dereference, you peek the outer pointer and then peek the thing you get from that.
Gotcha.
If
So-
you have a pointer to a pointer A, so the peek will return an IO pointer from that.
Gotcha.
There's nothing to stop you from doing the deep peek or the deep poke, but you have to kind of be consistent with that everywhere. Make sure all of your functions always deal with it the same way.
So Alloca would only do a shallow deletion.
Yes.
Deletion is an overloaded term. It will,
remove it from my.
yeah, if you do alloca of pointer to int, it will not allocate the pointer and then have that point to a pointer's worth of memory and then have that point to an int's worth of memory. It will not do that second step. It will just allocate a pointer's worth of memory, and it's your job to nest an alloca call to initialize the rest of it. Same way I think the idiom is to do multidimensional arrays in C. You first new a thing and then you iterate over that and set each one to new of whatever. Right, so you have this. I think I have an example. Yes, I have an example. And this does work. I tested it an hour before. So standard struct date, int day month stuff, and a function that takes a pointer to a date thing. So here we have like the canonical type in Haskell that we'd like it to have. And it's important to note that when we map types from Haskell to C, it's not like an overlay mapping, in that when we create a one of these from a one of these, we're copying each of these fields into Haskell land. It's not a, like, this int is not actually this int, it's a copy of the value. So now we can basically say that this is storable as a this. And now the point is that as far as the ABI is concerned, this name basically doesn't exist. It's equivalent to the size and the alignments of the various fields. It's just a set of bytes. And if you write the bytes to the right location, anywhere where a struct date is expected, it'll work just fine. So size of. There are 3 integers. The size of this struct is 12. And if that seems remarkably arbitrary and hard-coded, it is. Alignment is 4 because reasons. I will get into all of that in a bit. Here's an example of peeking, so reading from a chunk of data. So we know that the first field, that is day, is located at offset 0 from the pointer. So this function is in Storable. It's in this soup of things, and you only need to implement one of peek or peek byte off, or there's one more, I think. And yeah, so we're doing manual pointer advancement and stuff, and we're getting DMY, and we're creating a date out of that. Same thing for poke. We are just calling the underlying cint peek and poke functions. It's pretty straightforward. The only non-straightforward part of this is the hard-coded numbers, right? Yeah.
It feels really brittle to do it this way.
It is really brittle to do it this way.
Well, I mean, is there any sort of libraries that kind of, because you can take like, well, I guess you can't.
This is like the last 3 slides of the talk. So this is like, I'm doing FFI from first principles. There are tools and things on top of this to make it easier, also to deal with platform specificity and stuff like that. But this is the way I learned FFI, because those tools didn't make much sense. They have a lot of syntax, and if you need all of those features, that's great. If you don't, it's easier to write this directly.
So somebody changes the order of the struct.
Exactly, yeah. And so having done this, we can do foreign import of print date and give it the type that we know it's supposed to have. And now we can call alloca. So here, we've got a function that takes a p and pokes into it the date 1/1/2020, and that's how it knows that this p is of type date. And so alloca can then use that to allocate the correct amount of memory, which is 12, and then we can pass it to print date. All good? Great. So use alloca if at all possible. It's scoped, it's generally safe. I've stopped caveating everything because things can go horribly wrong, but like in general, this is safe. Like I said before, malloc, the pointer will be collected because it's a Haskell value, but the memory that pointer points to will not be collected. And so you need to pair mallocs and frees if that's what you're using. But unlike in C, Haskell does have a garbage collector, and even though the GC can't be relied upon to collect that memory, you can hook into it to help you collect the memory. So here's a more realistic C API. You have a struct. It has a pointer inside of it that points to some dynamically allocated buffer and some size. So this is a basic string class. But more to the point, you have an API which consists of creators and deleters. And here you give it a size, and it allocates the object itself and the buffer and returns that pointer to you. Save comments about my C code till the end of the talk. The point is that you've got an interface to everything. You've got functional interface to creating and deletion, and this is a lot of a simpler interface than having to call malloc and free directly. And so here, we can avoid writing storables because we never actually need to know how big a chunk of memory to allocate. Because we, as in the Haskell codebase, never actually allocates a foo. We only ever allocate foo pointers, and those are easy because we know how to allocate pointers independently of the types they point to. So this is an idiom, but I like doing it, is even though we never have to deal with foos, I like creating a data foo as an empty data decal. It lets you distinguish at the type level between foos and pointer to foos, but also quite clearly states that we will never be able to create a foo in Haskell. Right? We will only ever be able to create pointers to foo. Then we can foreign import the create foo function, give it the type that you expect it to have. We also import delete foo. And the ampersand here is part of that imp-ent grammar a long time ago. It's basically saying there's a function there, but import not the function to be called, but as a function pointer. So import me the address of that function. And it's imported as a finalizer pointer, and that's just a type synonym, as a function pointer to a function that takes a pointer to A and returns IO unit. So it's a destructor. This is in the standard library, like this type synonym is in the foreign.pointer. It's a useful, useful synonym to have.
Why import it as a function pointer rather than a function?
Because we are going to pass it to new foreign pointer. And that's the thing that it takes, and I'll get to that now. So here I'm introducing this thing called foreign pointer. And so foreign pointers are basically pointers with attached destructors in Haskell land. So there's no C-level guarantee of anything, but in Haskell, what it's saying is I'm pairing with a pointer a function that the Haskell GC is supposed to call when that pointer goes out of scope. And that function is supposed to clean up the memory. And so this is just like a C++ constructor-destructor, but it's this bastardized thing where we're getting the destructor from C land, but the logic of when to deallocate is in Haskell through the GC. Do I have a, yeah. So new foreign pointer, it takes a finalizer pointer. Like, this is a standard library function, and it takes a function pointer. And it takes the pointer that is the raw pointer with no attached memory management. And it returns you a foreign pointer.
Are finalizers guaranteed to run?
No.
There.
Sorry.
Yeah.
Right.
Yeah, I mean, this is right there. You cannot, the finalizer is not guaranteed to run. It's not guaranteed to run in any order. It may never run. I don't know what guarantees there are. Probably the guarantee is that, not a guarantee, but the implementation detail is that if you won't run out of memory while there is a finalizer left to be run. It's probably the same thing to assume. Yeah.
What's the or with any side effects? Because you're free in the destructor, which is the side effect.
That's mostly to do with ordering. So I think I mean just ordering. So if you have like printf statements in there, you can't rely on the ordering of different frees or different finalizer pointers going out of scope to the order. You can't correlate those with the order in which the printfs are called.
Okay.
Because it's at the mercy of when GHC decides to GC the pointers.
Why is there a distinction between function pointers and pointers at the type level?
They aren't actually that similar in CAPI. You can't just give a function pointer where it's supposed to point at C.
That's not at the CABI level, that's at the C source level.
I mean, because a function pointer in Haskell is like, well, a function in Haskell is a closure, whereas in C++ it's just an address to something we jump to. I think
But
actually
these
has
function pointers are C pointers to C functions.
well, I
They
think
can also be
Haskell
closed, too.
actually creates a function object for each closure it builds, and then gives the address of that object to the C function. Is that right?
That's not true.
That's not true. Okay, that's wrong.
The reason they're differently represented, I understand, is just to give you a few more utilities on being able to easily convert function pointers into callable functions. Like in C-land, if you have a function pointer, you have a syntax for calling the function, right, with the function pointer. If you import, I haven't tested this, so don't quote me on it, but you can probably import a function pointer as a regular pointer. But if you want to do anything that's specifically function-y about it, you will need to go through a bunch of steps that function pointers have already done for you.
I mean, it seems kind of similar to why you have phantom types, right? Like, you want to restrict what you can do with it, even though it's really the same thing.
So in this case,
Is the internal representation of a function pointer a fun pointer and the pointer the same?
what are the last two? Function pointer and
Fun pointer and pointer.
fun pointer and pointer are probably the same representation. Foreign pointer is not, because it has an associated list of things to call. And there is like a unsafe foreign pointer to pointer conversion that will get you just the pointer of the function. That we will look at in a bit. But yeah, foreign pointers, don't assume that the destructor is actually called. I've run into this problem when trying to debug what is happening and put printf statements, and don't rely on it. So again, valid with a caveat that you can do weird things, but in general, it hasn't been deallocated. So you can work with foreign pointers, and this is where you run into this problem of the function that you're importing is not the function you want to expose more generally to your code base, because one of them is the raw function with no attached memory management per se, and the other one is. So here we have some useful function that takes a pointer to foo, but I don't want to give it or rather the function I want to expose is the one that takes a foreign pointer to foo. So in this case, I need to unwrap it. And so with foreign pointer is a function that takes a foreign pointer and a function that takes a pointer and wraps it to take a function foreign pointer. The interesting thing that with foreign pointer does is it makes sure that the memory is not deallocated during that call. So make sure that the finalizers are not called. But this ultimately is the idiom that ends up making it into most of my FFI code is foreign pointers. Yeah, so boilerplate. There's a lot of boilerplate here. And I had hard-coded numbers here, all bad stuff. Platform specific, a lot of the times. But as I was just talking with a bunch of people before the talk, a lot of these numbers and things, there's only one reliable way to find them out, and that is to ask the C compiler what they are. You're not really going to be able to tell otherwise. And so that is in fact how I found these numbers. I mean, we can probably guess, but I ran a C program and I created that struct and I told it to print out size of that struct. And also the addresses of each of the fields to make sure that they were 4 and 8 offsets and so on. You don't want to do this manually. So things that are boilerplate are things like getting the size and alignment. Also, if you know what the arguments to a function are, you can figure out the function type as well. And you also have this API part with the reasonable pairing between allocators and deallocators and so on in larger code bases where this is not a toy example. So you'd like tools to do that for you, and that's where you use a preprocessor. So, interesting. Preprocessors are tools that process like a Haskell-ish thing with embedded annotations of some kind and generate more Haskell code with the appropriate FFI that we've been talking about. So all of the FFI incantations I've shown you throughout the talk are the thing that ultimately GHC processes. Everything else is something on top of that. So C2HS and HSC2HS are two tools. They come with things like this macro, which given a C type looks up its size. And the way it does it here, I've got a snippet from the manual, is it generates a C program and compiles it and runs it, which gives you the values that you need to put in back into your Haskell code. And that's ultimately the only safe way of doing it. And so from a platform-specific point of view, if you use C2HS, then it will regenerate that program on each platform, and so the numbers will be correct and so on. Yeah, I have used this a bit, but the first time I was getting started with the FFI, there was too much funky syntax here, and so I didn't understand what was going on, so I started writing the underlying FFI code directly. But in the future, for a production code base, which requires a large number of struct definitions and stuff, I would probably use one of these two. C2HS, I believe, is more featureful and more complicated, and this one is the other side of that spectrum. Yeah. All right. So, a couple of idioms, things that I learned. You should probably, if you're wrapping a library, if you're writing bindings to a C library of some kind, don't try to combine the writing of the FFI code with the Haskell abstractions. So don't try, so in the same way that we had foos and foo pointers, do a first round where you faithfully model exactly the data model at the C level, and then write a separate Haskell layer on top that encapsulates that stuff. If you try to hammer everything into one round of Haskell code, something will go wrong. We already talked about this before, but if you don't ever actually allocate a type, you don't need to write a storable for it. A lot of production code goes that way, which makes things a lot easier because you don't need to worry about size of and stuff like that. You may need to write C routines. So suppose that like 90% of the code that deals with a certain like date struct always deals with date star, but 10% works with an actual date. And so you don't want to write a storable instance just for that 10% of code. So you can put the interesting bits in the C side and write C routines that heap allocate the date struct and wrap functions that take values and turn them into functions that take pointers. Cabal, this is a common pattern. and there's some CAPI integration, at least from a convention point of view, to put this stuff in a cbits directory. And there is CAPI integration for all of this. I haven't gone into that, but it's relatively straightforward. That's it. Any questions, comments? Yeah.
How terrible is it debugging it when stuff goes wrong? Like, does it have ASAN, MSAN type stuff, or?
That isn't under the purview of the FFI. Like, I think that kind of debugging, and most kinds of debugging that I've had to do, you can use regular C debugging tools on the C library. When you get to writing the Haskell FFI bindings, you should only be in a position of debugging the marshalling and unmarshalling. So if you're at the point where you need to run C debugging tools through the FFI, you should probably do that in C first. It hasn't been that hard. I've still been able to run GDB, Valgrind, stuff like that on Haskell programs that call into the FFI. And in the segments of the Haskell program which call into C, they work fine. And sometimes I see some Haskell internal bits during the other parts of the code. The debugging experience is as good or bad as it would be for the underlying C library. No?
So,
Yeah, go ahead.
so C code, I guess this is just sort of following up on something I said earlier. If it accepts a function pointer, you can give it an arbitrary function, Haskell function, even if that function's a closure, right?
If a C function takes a function pointer, you need to give it a function pointer. That function pointer can be a function pointer you get from the C code itself, or you can create a function pointer out of a Haskell function. And so two of the bits I didn't go into were all the way back at the beginning, not there. So there are two special kinds of imports. One of them is called wrapper, and one of them is called dynamic. So if you, I don't know what is the utility of putting them in the foreign import. Basically, you can ask GHC to give you a function that takes a function of a given type and returns a function pointer of an appropriate type. This is one of the cases where any function in the C land that might call that function that you have wrapped needs to be marked as safe. The specific example that I had was there was a class that had a getter and setter for a global variable that was a function pointer to a function that could be used to format various bits. And so it was like a vector, and the dimensions, it was a pretty printing of a vector. And so I wanted the function to look up dimension names from a state monad that I had. And so I would write a function that in the state monad looked up those names. But then I'd need to pass that closure into C land. And if it's not marked as safe, then that function will hang. Or the call to the function that prints will hang.
Thank you.
Yeah.
Can you manipulate Haskell data types in the C? Like if you have a giant tree in Haskell that you're doing stuff with, and then you want to speed up a part, like can you pass that tree to C and like manipulate it there?
Yeah, this isn't something I've done, well, any of. But that's the export, that's part of what I believe is the export side of things. In that there's a C header file called hsffi.h, and it exposes some of the functionality of how to call Haskell functions into C land.
I don't think you're going to have much luck manipulating Haskell data structures.
Yeah.
There's all kinds of fun things with like, you have to force stunts and stuff.
Yeah.
But yeah, and follow in directions and.
I mean, you probably would
Seems nasty.
serialize.
I don't think the interface is there.
Yeah.
Yeah, the more likely
So I
thing you'll want to do is to marshal it.
I think the thing you can do is you can cook up like an opaque handle that you can pass to C, And when you get it back into Haskell land, you can export things that take these opaque handles and do operations on them. So you can have like an abstract interface to your data type and use it from C.
You could like give Haskell back instructions to run. You'd be very unlikely, even if the interface existed, you wouldn't be able to manipulate a Haskell data structure faster in C than you can in Haskell. Because that stuff's already optimized.
I mean, it might make sense, like if the C code was doing some other computation and needed to update a Haskell data structure where you're exposed to it like an immutable API to your Haskell data structure.
I do not trust any.
Yeah.
Haskell objects.
For scientific computing, have you noticed any sort of performance penalty going across the foreign function interface?
The performance penalty has been insignificant compared to the performance advantage of using the library compared to what I could have written in Haskell. I don't think there's that high. I mean, the vast majority of performance penalty comes from the actual marshalling, right? The copying of the data back and forth. And depending on the type and the size, that could take time. But calls themselves are not very expensive. So in my case, it was less from the performance point of view, more that there was just this established library that did the things I wanted to do, and I did not want to re-implement them. Anyone else?
In most of the examples, I saw a bare C file and bare Haskell file.
Yeah.
How much more difficult it is it to link to like a shared object or a static library?
Yeah, so most of my examples, initially when I tried them out, did link against .a and .so files, because I didn't realize that GHC could take .c files on the command line and build it themselves.
Gotcha, okay.
So I built it with GCC myself, and then just specified .so at the end there, and it worked.
You didn't have to like fudge with the include paths or anything like that.
For the simple ones, like it didn't need any custom include paths, but for the work I do regularly, I have pre-built a thing.
Gotcha.
And it's in my LD library path. And with at the bottom on the Cabal integration, I had extra libdirs, and that contains the path with my .so files, and that's where it gets it from. So you can do your standard things of like swapping out your LD library path for a different version if you want to test both the C library and the Haskell stuff at the same time. So you don't need to pass in the source code. It's meant to work at the level of the library.
Can you have different foreign implementations for different, I guess, ABIs? So like one for C, one for WASM or something? Or do they have to be different and then like you if def? Yeah.
Is there a straightforward way to like configure your code to, if you have some external library, so that it adds the path for you?
You mean the path to the SO files or the?
Yeah, rather than having to.
So one of those arguments at the very end, and extra libdirs, extra include, those are arguments to Cabal configure.
Well, I mean like a system library.
Cabal has some integration to work with autocomp stuff.
Oh,
okay.
It's it's not great, but it's what you have in the C world, which
On Unixes.
yes.
Thanks.
Not going to work on Windows. So it's not going to work on Windows.
all right. Thanks.
Thanks, guys.